Hello, everybody. My name is Samuel, and I'm here today with 3D Space Model Rocketry, and I'm here today to give you an update on the lawn dart rocket. So the lawn dart rocket, we've made a couple changes from Mark IV to Mark V. The changes being adding rail buttons, lengthening the fins back up. Here's the Mark IV, and then the Mark V is right here. It's a pretty noticeable lengthening. It's going to give us some more stability, and it's going to allow us to have a little bit more margin for error in the launch process. Now, you may notice that the rail buttons, they're kind of the breadth of the rail buttons. That is not very, it's not a very wide rail button stance. And that is because usually you want the rail buttons to straddle the center of gravity. But in this rocket, the center of gravity is going to be right about here, so we need a rail button like up here, but that introduces problems with adhesive and just getting them lined up perfectly straight. So, and that also allows for when you're in the launch rail and the first button goes out, then you're still accelerating, but you can tip over because the stability, you can't stabilize the rocket. Now, our rocket's gonna be moving very fast, but this can still be a problem because gravity is almost instant, and well, it is instant. It just so it can tip over but not allow it to stabilize itself, and so the lesser gap allows us to be in the launch rail for the longest amount of time for the motor burn, for both the rail buttons to be in the rail for a very long time, in relation to like the acceleration and the velocity and stuff like that. It allows us to have it allows us for a little bit more of a error. It allows to not it allows it to not allow it to tip over easier. So it's technically more stable by a little bit, not too much, but every percent of margin we have, that's an extra percent of margin that we wouldn't have gotten if on our previous design. Now, there's been another big change. We are going to be changing the material from PLA, it's very, very brittle, especially in these very thin parts. This is only, if it would focus, this is only one layer. It's like 1x2, so it's not very, there's not very much layer adhesion surface area for it to adhere to the next layer. And as you can see, this one has already started to crack, even with the minor handling that I've done with it. So we're changing the filament, the material, to PETG because A, it's stronger, it's less brittle, and B, it's more high temperature. So the tip on the rocket, it's a little bit dirty because I did some aerodynamics testing in the lawn. the tip can get very hot very fast, especially in the transonic regime where a rocket is going to spend a whole second. Now that might not seem very much, but it's very long to be transonic, Mach 1, Mach 1.3, and that's going to be a lot of jitter in the fins, and it's going to be a lot of compression in the nose cone, and that's a lot of time for it to melt, and then you have an unsymmetrical aerodynamic surface, and that's not very good. So that's another change, and we are also gonna lengthen this end cap right here that goes on the bottom of that screws onto the bottom of the nose cone, and so that allows for there to be more resistance inside the tube. Now, because the reason you want more resistance inside the tube is because, first of all, there's positive air pressure inside the tube. At ejection, our rocket's going to be around 4,800 feet ish, above the launch above launch conditions, roughly 4,800 feet above launch conditions. So that means and that's about 2-ish psi, roughly. It's 1.5 psi. That may not seem very much of a difference, but it's very much of a difference, because if you have one square inch of surface area, that's to push against inside the tube, that's 2 pounds of force. That is just the ambient air pressure inside the tube. That's just that trying to push the nose cone off before ejection. And then you add in the extra drag from the fins and the tube not constricting like an aerodynamic surface, it's not going wide and then constrict. It's going wide and just staying wide. So that's going to add some surface drag. That adds a little bit of surface drag because air doesn't want to stay decompressed like that. So that you also have drag on the fins in the tube that's also which is much less than on the nose cone, which is also trying to separate the nose cone from the fins. And so that if you lengthen this, and then you can also probably add a quarter of a rotation of blue tape or something like that. That allows you to get much more friction in the interior of the tube, and it allows us to get a much more firm grasp on the tube during the very long ascent. The burn time for the rocket, that's only about roughly a ninth of the actual time that a tenth of the actual time that the rocket is going to be ascending. So you have to keep the nose cone on for that additional 13 seconds. It's technically going to be still going up, but that's the biggest delay we can get with our G80. So you have 13 seconds that you need to keep the nose cone on while you're ascending. So we have longer fins, rail buttons. Even though they're incorrectly placed, they are, in this situation, they're the best option. incorrectly in quotes, and the new material, PETG, much higher strength, much higher heat resistance, and then we also lengthen the shoulder for the nose cone. So the reason we need this to screw off is we're gonna put an Estes altimeter in here to hopefully, if we recover this, to get the altitude, the actual altitude back when we hopefully recover it. So this is just a small update for the Lawn Dart rocket Mark 5. We are gonna hopefully come out with a build video and just integrating the fins and printing and doing all the fun stuff for the rocket to an integration video. Hopefully after this one, probably I'd say we're gonna be shooting for a week after this video, and we have a very big project that we are going to showcase probably a week or two, probably 2 weeks before we can get even just like a draft of the next video, because it's a very big project. And as you can see back there, this is my hand, like roughly for scale. Those are some motors that we're going to be using for the next project. So I hope you enjoyed me rambling about our rocket. I'll probably try to so I hope you enjoyed me rambling about our rocket, and I hope you see us, tune into our next video.